So this is the last review session for the final. So in this one, we're going to be going over the commonly missed questions from exam 2 version 2, as well as exam 3. So the first question we're going to go over is simplifying using exponent rules. Okay, so this question right here. So we have powers of A, B, and C in the numerator and the denominator. So the first thing I think that's easiest to do is just kind of to split it into looking at A, looking at B, and looking at C. So remember, everything here is multiplication and division, and those work together nicely. So we can split this into one fraction, A to the negative 5 over A to the 1. And you don't have to write out A to the 1. You can just leave it as A. You can just leave it as A. And there's a question in the chat, but I'm going to finish this question and then answer it. So yeah, you can just leave it as A or A to the 1 if you want. And then we can split B into B cubed over B to the 0 is 1. So I'm going to go ahead and rewrite that B to the 0 as 1. And then we can split it into multiplying by C. So C squared over C to the minus 4. So we have these three variables that we're dealing with, A, B, and C. So I'm going to split it into this product of 3 terms. And so now we can look at what happens with the exponents. So remember that our exponent rule is that whenever we divide, if we divide terms that have the same base and different exponents, you're going to subtract the exponents. And similarly, if you multiply 2 terms that have the same base and different exponents, you're going to add those exponents. So when we simplify this here, this turns into A minus 5, and then we're going to subtract that 1 on the bottom. B cubed over 1 is just going to be B cubed, and then C is going to be 2, and we're going to subtract that negative 4 from the bottom, minus 4. And now we can simplify it more. So this is going to be A to the minus 6 times B cubed times C, 2 minus 4. So we know that this is really adding the opposite. So this is really 2 plus 4. So this is C to the 6th. So this gets us most of the way there. However, you'll notice in the directions that it says to only have positive exponents in our answer. So B cubed and C to the 6th have positive exponents, but we're missing a positive exponent for A. So if we need to change an exponent from positive to negative or vice versa, we just flip where it is in the numerator or denominator. So A to the minus 6, oh, sorry about that. A to the minus 6 can be written as 1 over A to the 6th, and then everything else stays the same. So this is written as B cubed C to the 6th over A to the 6th. And so this is how you write that using all positive exponents. There were a good amount of people who didn't see the direction to only write it using positive exponents in there. I think exponent rules are just something a lot of people struggle with in general. But we have this relationship where division corresponds to subtraction and multiplication corresponds to addition. And then in this case, anything to the first power is just itself, and anything to the 0th power is 1. Okay, so the next question is part B. So this one, we only have one variable, only D here. So in this one, we're just simplifying it using the order of operations. So we're going to use the order of operations here, where multiplication and division are grouped and addition and subtraction are grouped. Okay, so there is a set of parentheses in this question around 3D to the negative 2, but there's no operation in those parentheses for us to perform, right? It just has the parentheses around that one term. And so because there's no operation that we can do inside those parentheses, we're going to go ahead and move on to our exponent. So we have negative, And remember, if it helps you to think about it, to remember how to deal with this negative in the order of operations, you can just write it as a -1 with multiplication out front. So we can go ahead and rewrite this. So that way we know for sure we need to do that exponent first. So the exponent rule that we have whenever we have something with the same exponent in different bases is that we can split that over multiplication. So we can split this into 3 cubed and d to the -2 cubed, right? So because we have the same exponent in different bases, we can split multiplication like this. I went ahead and put the parentheses around the d to the -2 just because we have double exponents there. So just to make it more clear what's going on. So then this is evaluating our exponents. This is 27 times. And then when we have one exponent raised to another, we're going to multiply those exponents together. So this is d to the -6. And then we can write this as -27 d to the -6, combining it all. However, just like part A, we need to only leave positive exponents in our answer. And so we're going to write this as -27 over d to the 6th, moving it to the denominator to get that exponent to be positive. Okay, so this is how, just kind of a review of some exponent rules of how you simplify different things. So are there any questions over how to simplify things using exponent rules? Okay, so there was a question in the chat about the structure of the final, and I will get to that. I'm just going to get to it at the end after we work through the problems. I'll talk more about the structure and the layout of the final at the end. Okay, so another commonly missed question on exam 2 version 2 was dealing with operations with fractions. So these are both questions about multiplying fractions. So the first one is 21 over 32 times 16 over 27. So remember that our multiplication algorithm for fractions just says to multiply straight across. So this is 21 times 16 over 32 times 27. So we just multiply straight across, and you'll notice that these numbers are typically picked so that you can cancel them out. So the extra direction on this question is to write your answers in the simplest form. So like I said, these numbers are picked so that you don't have to do some outlandish large multiplication and then division that just seems really complicated. So you can see that there's a relationship between 16 and 32, namely that 32 is 2 times 16. So those are going to cancel out nicely. And there's also a relationship between 21 and 27. Those are both multiples of 3. So 21 is 3 times 7. And then we still have that 16. And then 27 is 3 times 9. So they're typically going to be common factors that you can simplify. So the 16s will cancel and these 3s will cancel. And then we have 7 over 2 times 9, which is 7 over 18. And if you've canceled out all of your common factors, that's going to be the most simplified way you can do it. Okay. So yeah, this one was just commonly missed because a decent amount of people went out and multiplied 21 times 16 and multiplied 32 times 27 and then tried to divide those things. And that costs a lot of time and energy, but we don't need to do those things. There's typically going to be a quicker, easier way to do things. Okay, so the next fraction question here, so you'll notice I didn't pull all of the parts from question 7 just because there were a lot. I just pulled these two that I think people struggled with more than others. So the next one is multiplying mixed numbers. So I'm going to write in red the common mistake. So in the last session, we talked about how to add and subtract mixed numbers. And in that algorithm, we deal with the whole numbers and the fraction parts separately. However, that is not the case with multiplication, and I'll show you why. So we can remember that mixed numbers have this implied addition here. So this is really 3 plus 2/3 times 2 plus 1/5, right? So the common mistake is to do the same thing that we do with adding and subtracting mixed numbers and deal with the whole numbers and the fraction parts separately. And that's not going to be the case here because we need to distribute. We're going to need to, if you like to think of it as foiling, you can think of it as foiling, but we're going to need to distribute this because we're really going to look at 3 times 2 and 3 times 1/5. And then we're going to look at 2/3 times 2 and 2/3 times 1/5. So we actually have 4 multiplications going on here. And so we can simplify all of these things. So 3 times 2 is 6. 3 times 1/5 is 3/5. 2/3 times 2 is 4/3, right? I'm just multiplying across here. And then 2/3 times 1/5 is 2/15. I think the easiest way to add these is going to be to get a common denominator. So when I do that, we have 6 plus the common denominator here being 15. So we have 9/15 multiplying by 5 on top and bottom. And then we're going to have 20/15 multiplying by 5 on top and bottom. Then we have 2/15. So when we add all these up, 9 plus 20 plus 2 is going to be 31. 31/15. And we know that we can rewrite this 31/15 because 15 times 2 is 30 as 2 and 1/15. So we can get 8/15 here as our final answer. So this way of solving the question uses distribution. I'm pretty sure on the exam 2 version 2 key, I do it a different way. So the way I do it there is to convert each of these mixed numbers to improper fractions. So our multiplication 3 and 2/3 becomes 11/3 and 2 and 1/5 becomes 11/5. And so you would multiply 11/3 and 11/5 together. So that process is a lot shorter. But recall we talked about in one of the previous review sessions that sometimes you're going to be asked to do things using either mixed numbers or improper fractions specifically. So you should know how to multiply these mixed numbers by keeping them as mixed numbers and multiplying them as improper fractions using the typical multiplication algorithm for fractions, which is just multiplying straight across. Yeah, this one, like I said, commonly missed because people tended to treat the whole number part and the fraction part separately, but you can't do that because there's this distribution going on. Okay, are there any questions about these questions over multiplying fractions? Okay, so next we're going to move on to exam 3 version 1. So the first question is to subtract integers using a number line. So this is an example of doing operations with integers using a model, and that model being number line. If you have struggled at all to see how the topics list relates to the questions, this is subtracting integers using a model. Okay, so whenever we subtract things using a number line, we obviously need to draw a number line. So I'm going to go ahead and say the first step is to draw a number line. And I'm going to go out to negative 12, 11, 10, 9, 8, 7, 6, 5. I always draw it too short. 4, 3, 2, 1, and then we'll stop at 0. Okay, so there's multiple ways to go about this. So some people, whenever they do number line models, they always like to start at 0, but I don't think you necessarily always have to start at 0. As we saw whenever we went through this in the lecture videos, is that you can just go ahead and jump to start at the first number facing right. So a lot of people didn't put the direction that they were facing in this model, and that's kind of the whole point for using this number line model with integers, right? We had a similar number line model with whole numbers, and because we didn't have negative signs with the whole numbers, we didn't have to talk about which direction we were facing. So if you wrote this as if it was the number line model for whole numbers, you got points off if you didn't say which direction you faced or why you changed direction. So we start at -9 facing right, because you always start at the first number facing right, just because we always like to move positively, and the right facing right is facing the positive numbers that are bigger than you. So next, we encounter a minus sign. So we dealt with that -9. Well, I'll do it in black here. So we've dealt with the -9, and that's where we start. But next, we encounter a minus sign. And remember that anytime we encounter a minus sign or a negative sign, we're going to change directions. So we're going to change to face left due to the minus sign. You may have also noticed a comment on your exam of a distinguishment between a minus sign and a negative sign. So I talked about this in the lecture videos, that this is a minus sign because we're subtracting 2. It's not a negative sign because we're not adding -2, right? There's a subtle difference there between subtracting 2 and adding -2. And although we know that those are the same, again, I think the language is really important for you to kind of practice using this precise language for whenever you teach this to students hearing it the first time. If you say things that you know are true, but your students don't know are true, it can really confuse people. So we encounter a minus sign, not a negative sign, and change to face left. And then next we encounter this 2, so we move 2. We're going to move 2 units from 9 right here. So we're facing left, so we're going to move left 2 units, and we are going to end at -11. So this last step, you don't really need to say where you end, but you do need to tell me what the answer is. We're explaining how to subtract these integers using the number line. Although you should explain how to do it, you should also tell me what the answer is, right? So -9 minus 2 is -11. Okay, so the answer is important. The explanation is also important. If you missed the explanation, you obviously got points off. If you didn't write the answer to the question, you got points off as well. Okay. Were there any questions over using this model for this question?
On when you said move 2 units, so is it not necessary to say move 2 units to the left because we're facing left already in the previous step? Or?
Yeah, I think it depends on the context, right? So because I already like explicitly said that we're facing left, then you would move 2 units in the direction that you're facing. But yeah, you're probably right. It's always better to be safe than sorry and say which direction you're moving if you're going to move on the number line. That's a good point. Any other questions on this one?
I have a question. Does it matter where you start on the number line? Like I know you started at -12. Just depending on the number or the question, does it matter how many numbers you have on the number line?
Yeah, so looking right here, right, the leftmost number I had was -12. No, it doesn't really matter. I mean, because we know how to do these operations in our head pretty quickly, I knew the answer is going to be -11, so I just went 1 over. But as long as all of the numbers that you care about in your problem are on the number line, it doesn't matter how far you go. People typically, right, on this rightmost number being 0, people typically just like to have 0 on the number line so they can see kind of where the middle is. But yeah, it doesn't matter.
Okay, thank you.
Mm-hmm. Okay, so the next question deals with solving an equation using rational numbers. Okay, so, and this is the topic that's listed on the topics list, I'm pretty sure, solving equations with rational numbers. That's from chapter 9. Okay, so solve with justifying each step. So we need to justify each step and also check our answer. And the answer may look funny, right? That's just a disclaimer that it may not be a nice whole number. Okay, so the first thing we do, so a lot of people wrote on their exam 3 to use the reverse order of operations, which is great. That's typically how we solve things like this. So when we start doing our reverse order of operations, the first thing we're going to do is subtract 3 from each side. So when we subtract 3 from each side, that 3 on the left goes away. And then we're going to subtract 3 from 27. I'm actually not going to number these. And then we're going to simplify. As I mentioned in one of the previous videos, it never hurts to just throw in simplifying between each step. So now we have nothing else that we can add or subtract to cancel out. So we need to switch to multiplying and dividing. You can do this in different ways. There were some people who converted 1.2 to the fraction 12 over 10, equivalently 6 over 5, and then multiplied by the reciprocal, which is a great strategy. You can also just divide these decimals depending on if you are more comfortable working with decimals or fractions, because it doesn't say to use a specific algorithm to do anything. You have the liberty to pick if you prefer to work with decimals or fractions. I'm just going to stick with decimals. So next we're going to divide 1.2 from each side. So we're going to have x. The 1.2 cancels on the left, and then this is 24 divided by 1.2. So I would speculate that a reason that a good amount of people change these to fractions is because they don't like dividing by decimals, because the algorithm they may not have remembered. But remember, this is a fraction, which we can multiply by 10 on top and bottom, which just equates to moving the decimal. So this is the same thing as 240 divided by 12. And that's an easy division to do. So whenever we do our last step of simplifying, 24 divided by, or 240 divided by 12 is 20, right? That should be not too difficult to see. And in this last step of simplifying, you should actually simplify it to get a final answer. There were some people who stopped at this 24 divided by 1.2. You should go ahead and do that division because the last step in the steps to solve this equation is to simplify. So you should simplify the answer. Okay. Oh, and now we need to check our answer. So that just means to plug in x, what we got was 20. So whenever we do this, 1.2 times 20 is just going to give us 24. You can write that out to the side explicitly if you want, but I'm not going to here. So we're going to get 27. So the checking your answer part's mainly just for you to double check and make sure that you did your last steps correctly. Okay. Are there any questions about solving equations with rational numbers?
When we for the justifying each step, we need to write out like the move the decimal to the right on when you do 24 divided by 1.2?
Yeah, that's a good question. I wouldn't say so, just because this last step of simplifying, in my opinion, encompasses that doing the division 24 divided by 1.2, which that division algorithm has, the moving the decimal. So I wouldn't say that you need to write it out just because it's kind of implied in this simplification step. But that's a good question. Okay, so number 6 is writing word problems as equations and then solving them. So these, because you can see that they deal with saying percentages of numbers. So this means that we're going to use the percent equation because we're writing percents in equations. Well, the most obvious one to use is the percent equation, which has two different forms. You can either have it as the part is the percent times the whole, or you can have it as the part over the whole is a percent over 100. So either of these forms will work, just depending on your personal preference. So the first one is what is 40% of $5.50? So we're looking for a part here because we have our percent and we have our whole. So I'm just going to use the first form of the equation that says our part is the percent times the whole. So remember in this equation, A equals PB, we're going to write our percent as a decimal. So this is our part is our percent times our whole. So we just need to do this multiplication. So 5.5, I'm going to go ahead and take off that last zero because you can just take off any zero that's after the decimal place if it's your last digit. So we're going to do 5.5 times 0.4. So 5 times 4 is 20, write the 0, carry the 2. 5 times 4 is 20, plus 2 is 22. And whenever we multiply decimals, we count the number of decimal places. We have 1 here and 1 here. So our answer is going to have the sum of that, which is 2 decimal places. So it's going to be 2.2. So that says that A is 2.20. You don't have to write the 0 there, but you can. So then whenever we write out a final answer in words, we have that. Putting our units back in, that $2.20 is 40% of $5.50. So that's the final answer there. Okay. So the next one, 72, is 90% of what number? So we're given our part and our percent, and we need to find our whole. So for this one, I'm going to use the other form of the percent equation, but you can do whatever you prefer. So we're going to have that our part over our whole, so 72 over our whole, is going to be 90 over 100, because when you use this form of the percent equation, you write your percent as this fraction, like the equation says. Okay, so now we just need to solve it. So remember, this is one of the most important things I've said in this class is do not. I should have emphasized this more, and I apologize for that. I'm going to emphasize it now before the final, is do not cross multiply. So we're not going to cross multiply here. There are reasons for this, and they're been explained in the lecture videos. I think using people, I think when we went through school, a lot of us were just taught to, when in doubt, use cross multiplication. And I've seen people use cross multiplication instead of the multiplication algorithm for fractions, right? Multiplying straight across. Instead, I've seen people cross multiply, which is definitely not the right thing to do. So to try and mitigate issues like that, we're just never going to cross multiply in this class. So don't do it on the final because I'll take points off. We're not going to cross multiply. Instead, we can use equivalent fractions or clearing denominators. There's lots of other strategies that we've used throughout this course other than cross multiplying. Okay, so first I'm going to look at this 90 over 100 because I can simplify this, right? 90 over 100 can be written as 9 over 10. And if you notice, a lot of these questions are picked strategically so that the numbers are nice, so that you don't have to sit here and do things that are difficult, right? And it shows in that way because I'm aware that you don't have a calculator on the exam. Just like any of you who are going to be future teachers, you're going to pick problems that your students can do easily without a calculator because a lot of classrooms for younger students won't have calculators. So you can see that 72 is a multiple of 9. So if we multiply by 8 over 8, right, this is essentially multiplying by 1. So the value here doesn't change. This is going to be an equivalent fraction, so we can write this equal sign. So this is 72 over 80. So all of these equal signs are correct, where this first one comes from the percent equation. This one is an equivalent fraction, and this is also an equivalent fraction. Multiplying by 1 doesn't change anything because 1 is the multiplicative identity. So all of these equal signs hold. And this tells us that b is 80, right? You can just read it from the leftmost term and the rightmost term. 72 over b is 72 over 80. So that tells us that b equals 80. And so writing out our final answer, we have that 72 is 90% of 80. And that's our answer here. Okay. Are there any questions about using the percent equation?
I just have a quick question. Where did the 8 times 8 come from? Was that to get the 72?
Yeah. So whenever we were at this step where we had 72 over b just equals 9 over 10, you can notice just by looking at this equivalence here that 9 is a factor of 72 and 72 is a multiple of 9. So you can say, oh, I have my numerators as 9 and 72, and I know that 8 times 9 is 72. So it was just kind of a cleverly chosen way to make both of our numerators 72, because if your numerators are the same, then your denominators would be the same.
Okay, thank you.
Mm-hmm. Any other questions on this one? Okay, so moving on to exam 3 version 2. So here, one of the most commonly missed questions were actually the first 2 questions where we talked about the algorithm for multiplying and dividing decimals. So You do not line up the decimal places in either of these. When you add and subtract decimals, you line up the decimal places. When you multiply and divide, you do not at all. So let's go through it. We've done this before. So we've seen when you multiply decimals, we did it right here, right? And in this case, in a lot of cases, the questions that we are interested in are ones that have the same amount of decimal places. And that just happens to be the case a lot of time, but it doesn't have to be. So I understand that it can be confusing because most of the time the decimal places just happen to line up, but that's not the algorithm that we follow. So the first step is to line up the decimal places sorry, we're not lining up the decimal places. That's what we're not doing. So we're lining up the numbers on the right. So some people wrote out an example with this, which is fine. You can do that. You just also need to be able to tell me how to do it generally. So for example, if we're multiplying 3.21 times 4.5. So if we're doing this multiplication, we line up the numbers on the right. So we don't have to line up the decimal places. We just want them both to be aligned on the right, right? It's like whenever you're typing something, you can have a left align, centered, right align, or justified. We're right aligning them on the right. So the next step, also, some people just said to line up the numbers. Well, that doesn't tell me how. I know with some of our other algorithms, we've just said line them up vertically, which is essentially saying to line them up on the right. But just because there may be some confusion on lining things up with the decimal places or in some alignment, tell me that you're lining them up on the right. So next, we multiply the numbers. So we multiply the decimals that were given as if they were whole numbers. So what I had a lot of people do here is just say multiply them normally. And that doesn't tell me how to do it, just because the word normal is really subjective. Multiplying them normally doesn't tell me to multiply them as if they're whole numbers, right? Some people may consider decimal multiplication the normal way to do it. So yeah, if you put normal, you definitely got points off just because that doesn't tell me how to do it. But if you say multiply them as if they were whole numbers, that tells you use the whole number multiplication algorithm that we know. So using our example here, 5 times 1 is 5, 2 times 5 is 10, write to 0, carry the 1, 3 times 5 is 15, plus 1 is 16, cross out the 5, write a 0, 4 times 1 is 4, 2 times 4 is 8, 3 times 4 is 12. So we're multiplying them as if they were whole numbers, and then we're adding up the things. There were also a good amount of people just on the third exam who forgot to add these numbers or didn't add them. But this is how you do multiplication by hand. It corresponds to this addition as an intermediary step, just like long division, as we'll see in part 2 or in question 2 here. Division corresponds with subtraction. Those are correlated operations, as we've seen. So then back to the problem, 8 plus 6 is 14, write the 4, carry the 1, we have a 4, and we have a 1. Okay, so now we multiplied them as if they were whole numbers. So now we need to say we're replacing the decimal point. We don't just take the decimal point away and completely ignore it because these are still decimals. Our answer, most likely, if you multiply something that's close to 3 and something that's close to 5, you're not going to get this 14,000 number, right? We need to place the decimal somewhere. So the way we do that is we count the number of decimal places in the factors. So you could say this as counting the total number of decimal places in the factors, or counting the number of decimal places in each factor and then adding them. Those mean the same thing. So we're going to count the total number, meaning that we add them, the total number of decimal places in the factors. And then we're going to place the decimal in the product so that the product has that many decimals. Has that many decimal places. So this is the M and N that I commonly write. So in our first number, we had 2 decimal places. In our second number, we had 1 decimal place. Then we add M and N together to get 3 decimal places. And so we place our decimal there. So another way, I've said this in one of the previous review videos, but it's not too difficult to check yourself to make sure that your answer makes sense just by kind of rounding things, right? So 3.21, let's say it's close to 3, 4.5, it's close to 5. So we know that 3 times 5 is 15. So our answer should be around 15. And placing the decimal in that way does indeed give us what we want. So that's it. So you need to say how to line up the numbers, how to multiply them together, and then where the decimal goes in the answer. I will say this is another case in which using the vocabulary of factor and product just makes things easier. Specifically when we count the number of decimal places in the factors. Sometimes people will just say numbers and I'm like, okay, well, which number am I counting? Just in case there's some numbers that, right? If we have already multiplied them, we already had a lot of numbers written down. So which decimal places are we counting specifically? So yeah, just using that vocabulary can definitely help the clarity of your explanation. Okay, I'm gonna go ahead and do the next one. That's explaining how to divide 2 decimals. So again, you do not line up the decimal places. What we're going to do is, I know I've done this in a past review video, but I'm just gonna do it again, just because. So the first thing that we're going to do is we are going to multiply the divisor, which is the second number in the division, and the dividend, which is the first number in the division, by powers of 10, which is the same thing as moving the decimal place until the divisor is a whole number. So we're going to multiply the divisor and the dividend by equivalent powers of 10 until the divisor is a whole number. Then we use long division. And we place the decimal in the quotient directly above the decimal in the dividend. So we did this earlier in this session. So let's just use this as an example. This is 24 divided by 1.2. So if we have 24 divided by 1.2, if we move the decimal place in each of these one time, this is the same thing as 240 divided by 12. And if we do this division, 12 goes into 2 no times, 12 goes into 24 twice. with 0 left over. So we put a 0 here, and the decimals are going to exactly line up on top of each other. You don't move the decimal back. Although you do move the decimal place to perform the division, there is no need to move it back because, as we saw when we looked at this example earlier, we just multiplied a fraction by 1, right? We moved the decimal in 24 to get 240, and we moved the decimal in 1.2 to get 12. So these are equivalent things, right? We have this equal sign here. These are equivalent answers. So there's no need to move the decimal back because we know that these answers will be the same. So we changed the problem to an easier problem that will have the same answer. So there's no need to move the decimal back. Okay, are there any questions about multiplying and dividing decimals? Okay. So lastly, we have questions on simplifying these expressions. So for A, so whenever you're subtracting numbers, whenever you're subtracting decimals and the first number in the subtraction is smaller than the second number in the subtraction, I think it's easiest to avoid making mistakes is to rewrite this by factoring out a negative. So we have negative 7.34 plus 11.26. And if we rewrite this using the commutative property of addition, this is negative 11.26. We know that adding a negative number is the same thing as subtraction, minus 7.34. So we can rewrite it like this. And then this is an easier thing to do. So if we do 11.26 minus 7.34, so whenever we add and subtract decimals, we do line up the decimal point. So 6 minus 4 is 2. We cannot subtract 2 minus 3, so we need to borrow. 12 minus 3 is 9. We cannot subtract 1 minus 7, but we can subtract 10 minus 7, and that's 3. So 3.92. So this is negative 3.92. And that's the answer. So the next question is 2.30 divided by 0.7. Okay, so this was probably the hardest question on the exam. But a lot of people got a lot of credit, even if they didn't get the full answer. So using the division algorithm that we just talked about, this is the same thing as if we move the decimal. This is 23 divided by 7. If we move the decimal and both the divisor and the dividend once to the right. So now we need to divide 23 divided by 7. So 7 goes into 23 3 times, with 2 left over. And because this is a dividing decimals problem, we can keep going, right? We don't need to just say we have a remainder. Remember that anything you can just add zeros after the last decimal place. So that's what we'll do. So we can put this 0 down here and say 7 goes into 22 times with 6 left over. Bring a 0 down. 7 goes into 68 times with 4 left over. 7 goes into 40 5 times with 5 left over. 7 goes into 50 7 times with 1 left over. 7 goes into 10 1 time with 3 left over. 7 goes into 30 twice, 3 times, 4 times, 4 times with 2 left over. And at this point, so if you look at the remainders that we've had a remainder of 2, 6, 4, 5, 1, and now 2. So recall that the rational numbers, decimals are rational numbers, because every decimal can be written as a fraction using powers of 10 as your denominator. So recall that based on the definitions and the vocabulary matching that we had on this exam, that the rational numbers are, right, so the real numbers are all the numbers that can be written as decimals. And the rational numbers are the real numbers that can be written as decimals that repeat or terminate. So rational numbers have decimals, well, are decimals. That repeat or terminate. So the reason I kept going, so there were a good amount of people who essentially gave up on this question at some point and said, I'm not going to do any more of it. But we know that the rational numbers can be written as decimals that repeat or terminate. And this 23/7 is a rational number, right? A rational number is also a fraction where the numerator and the denominator are integers, where you're not dividing by 0. So this is going to be a decimal that repeats or terminates. You just have to eventually get there. So it's going to end eventually, or it's going to repeat. And recall that we know it's going to repeat once we get the same remainder. So now that we have a remainder of 2, if you keep going with this division, you're going to get a remainder of 2, 6, 4, 5, 1. And then you're going to get another remainder of 2. So this tells us that we're going to have a repeating decimal. We're just going to have this endless cycles of remainders, because once we have a remainder of 2, our next remainder is 6. So once we get back to 2 again, we know that this is going to repeat. So there is a correct answer, and we did know how to find it, although many people did not on the exam, that 23 divided by 7 is 3.285714, where that entire decimal is going to repeat, right? Because 7 goes into 20 2 times, and then it goes into 60 8 times, then 5, 7, 1, and 4, and then we're going to just keep going, 2, 8, 5, forever. So this was, like I said, the hardest question on the third exam that a lot of people didn't fully solve, but we have talked about how to identify repeating decimals, and you are expected to know how to do a question like this on the final. Okay, with that being said, I'm going to take the last few minutes and talk about the structure of the final. I'll also send this in an email. I expect the final to be 20 questions. So all of our exams thus far have been 20 questions and roughly 100 points. So I expect the final to be double that. So I expect the final to be 20 questions and 200 points. And you'll also have double the amount of time on the final. So typically we've had 10 questions out of 100 points, and I've kind of allotted 1 hour to do the questions and then 30 minutes to deal with uploading. So on the final exam, we'll have double the amount of questions and double the amount of points. And so I'm going to allot roughly 2 hours to do the questions and then 30 minutes to deal with uploading. So you'll have 20 questions, 200 points, 2.5 hours to submit it, which is the standard final time for anyone taking online. For anyone taking hybrid or in-person classes, the standard final time is 2.5 hours. So that's what we'll do as well. So are there any last minute questions over simplifying expressions or the structure of the final or anything like that?
On 4A, do we have to pull out the negative, or Can we just do like the 11.26 minus 7.34 that you did and then add the negative, or would you want us to show the work that?
Yeah, you don't have to show that you pull out a negative like that. You can just do 11.26 minus 7.34 and then put a negative in front. That's fine.
Okay. All right, thank you.
Any other questions over anything about the final? Okay, I'm going to go ahead and stop the recording.